I'd like to welcome everybody. Topic today is log-based storage, as you can read, and hopefully that's why you're here. My name is Mark O'Connell. Just start with, the disclaimer. It's a slightly different one because this is a tutorial rather than a regular conference presentation. You can read this, but my basic translation is, if any of you are going and you make either financial or business decisions based on this and it goes south, you can't blame me and you can't blame SNIA. However, if it goes well, I'd like a share of the profits. So let me know. Okay, so what are we doing? Log-based storage. Log-based storage, it's hardly a new concept. I think everybody in this room, if you've ever been a developer or anywhere else, you've used logs at some point in your life. So why are we doing a tutorial about them? Basic reason behind that is because traditionally logs have been buried within an application. And the application has used them for various purposes, but really they were kind of hidden from the end user. And they were there really purely for that application. And as time has moved on, people are basically realizing that the logs themselves have value and that we can implement logs in a way, taking advantage of some of the storage technologies, implement the logs in a highly efficient manner, then build other applications on top of it, which has the side effect it simplifies the application because it can use a standard log mechanism instead of having to build one itself. You can have multiple applications using that same abstraction. And then you get into all sorts of other possibilities, like multiple applications processing the same data, doing different operations with it, and things like that. So we're basically going to walk through a whole bunch of things about logs, traditional usage, how they lead up to that picture, where the logs themselves really become a first-class data structure. And people process the data on top of the log, and it's all stored, that's your single source of truth. So what is a log? Logs, these are used everywhere. They're used both in computers everywhere, they're used in the real world. How many of you at your place of work have a visitor log? Or when somebody comes in, they've got to sign their name and the time they came in. And presumably when they leave, normally they have to sign their name again. I think every company I've ever visited has that kind of structure. Access log is similar, arrival logs, and so on. Computers often have system logs. You look on a Unix system or something like that, there are logs of the messages that occurred. There could be boot logs of what happened when the system is booted. These are used very, very frequently just to record what happened in the system. So what are some of the characteristics of these logs? How do people use them? How are they stored and so on? First one is very simple. It's an ordered set of events. And that's normally one of the key things about a log, especially when you're looking back trying to figure out what happened. The log tries to unambiguously state A happened, then B happened, then C happened. And you're pretty much guaranteed that if they were in the log A, B, C, you at least hope that C did not occur before B. Now that's sometimes a little bit fuzzy because, of course, when B and C actually occurred and when they actually got written to the log, there's a bit of a gap in there. So maybe C actually did occur before B, even though they got written into the log in the opposite order. That can happen, and you need to be aware of that. You can do things like timestamping in the log and so on. So if you can capture the timestamp when the event occurred, maybe they get written to the log in the wrong order, but you can redo it based on the timestamps. So there's some tricks you can pull about that. But basically, a log is that ordered series of events. Generally, it's readable by a lot of people or a lot of processes or so on. That's not a hard requirement, but for the most part, you have different actors who are interested in what that sequence of operations was, and they're interested for different purposes. Generally, append only. And what append only basically means is the log becomes that immutable source of truth about what happened, and you can't go back and change the past. You could argue a little bit like an example I mentioned earlier about a visitor log, where I sign in and then later I sign out, and aren't I changing the past? That's arguable. On a physical log, it is normally done that way. I go back and I update the entry. In a computer log, you'd simply have two entries. Here's when I arrived, here's when I left. Logically speaking, it winds up being the exact same thing, but in a computer log, that's the more common pattern to preserve that property that the log is append only. Once something makes it in, it doesn't change. You're always writing at the tail end of the log. How about reads? You always reading from the end of the log? Not necessarily. If you want to see, who's left the property recently, you're going to read from the end of the log. But if you want to take a look at, how many visitors come to this facility every day, you're going to go way back in time in that log and process all of that data. So your reads can really pick up from anywhere. Or it may even be, There's an intrusion I later figured out, during this week. I'm going to again go back to that week, read that entire week's worth of entries, try to figure out what was going on. Somebody got onto this facility that they weren't supposed to. So your write pattern is these small little entries always at the tail. Your read pattern is all over the map. Now, one thing to note here, and this is a bit, CU was around yesterday. If you're at the blockchain tutorial, the blockchain beyond Bitcoin, I talked about some of the properties of a blockchain. They're awfully similar to this. A blockchain is simply that ordered series of events. A blockchain has some more characteristics around distributed consensus and things like that. But my personal feeling is there's a strong relationship between logs and a blockchain because they are very similar in that sense, that ordered series of events that you can use to analyze what happened. Now, there's some very big differences between them, especially in how they're used and things like that. But again, I think there are in some cases where that line may be blurred depending on exactly what you're trying to do. Okay, so what are audit logs, or what are logs traditionally used for? I think probably most people, again, I'm from the vendor side, very aware of audit logs in a system. We don't tend to use them so much ourselves, but they're extremely important for customers. Because what do customers want to do? They want to have a record of what operations have changed on their storage, who did what, when. And they want that operation, they want to make sure the system is capturing that, they can pull it off, they can store it, so they can look back and they can figure out when something went wrong, how did we get there? What was the mistake? How can we prevent it? Same thing with the debugging log. How many of you are programmers? A couple of you. How many of you have ever spent hours poring over a debug log to figure out what the hell happened? I've done that before plenty of times. My personal opinion, I've used real-time debuggers and other things. My best friend in all my sessions has been a good debugging log to help me figure out exactly what happened, what the order was, and follow the logic in the system. Same thing, databases and file systems, a recovery log. Again, I've never actually programmed a database, but I'm very familiar with the transaction subsystems and so on. How do you affect a transaction within a database? Typically, you write out a recovery log that says, basically, here's what I'm about to do. If I crash in the middle of it, I can go to that recovery log and say, okay, well, here's my state, here's what I was trying to do, and I can replay and move forward. It's complex logic and so on. It's one of the harder things to get correct, but it's that ability to record, here's the operations, and then play them forward. Same thing, a log-based file system. They do that exact same operation when they're flushing all their metadata writes out to disk. They need a way to recover quickly, because any of you, I see a few people with gray hair in here, anybody ever remember full FSCKs and how long they would take? Well, log-based file systems were fantastic because they cut down that whole thing. You didn't have to check the sanity of the entire file system anymore. You could just replay the operations in the log and you'd bring your system back up. Similarly, source code control log, again, I think you kind of get the idea behind this. Logs are incredibly useful to figure out what happened in the past, what do you want to do about it? There's an interesting question asked once by an author named Isaac Asimov, I'm sure many of you have heard of, in his story, The Dead Past. And the question he asked is, what is the past? Well, you look at a bunch of these cases, an audit log, you might be going back a few months looking at what happened on the system. A debugging log, you're probably going back a few hours, maybe a day or so, to look at what happened. Same thing, with a file system recovery log, maybe that's a few minutes. So is a few minutes the past? How about a second? Is a second the past? How about 10 or 20 milliseconds? When does it stop being the past and become the present? And the point about that is it different to look at a log for operations that occurred within the last 20 to 30 milliseconds versus looking at them in these cases? The basic answer is no. It's still that ordered set of records of what happened that you're analyzing and looking at and trying to figure out what to do. What's different about modern systems and what's coming now is a whole bunch of changes within the industry really taking advantage of the fact that you can have log-based structures with extremely small latencies between when an event is written and when you can go and process it. And that opens up all sorts of new possibilities for how you can be using logs in the system, how you can build systems based on top of a log. One of them up here is analytics. Open source implementations like Apache Apex or Flink, Spark, and things like that. What do? They look at a stream of data coming in, they look at the different events, they try to analyze it according to code that the programmer develops, make decisions about that. Clearly, if those events are a week old, it's more of a batch processing system. But what about when those events are 10 milliseconds old? You're talking real-time analytics at that point. Because a 10 millisecond delay, okay, in some like industrial applications and so on, 10 milliseconds could still be a lot. But for something like on a human scale, credit card fraud and everything like that, 10 milliseconds to do a quick real-time analysis for fraud, you're never going to notice. So all sorts of interesting applications that once you have this capability to put data in the tail of that log, read it out quickly, analytics, processing that, making very fast decisions becomes interesting. Also, what's in there is streaming, real-time streams based on top of this concept. And again, things like Apache Flink, Apex, and so on need a storage system or a system for getting that data. And that's typically other open source things like Kafka or Pravega that are designed around the fact of collecting data from a whole bunch of different sources, pushing them in an append-only fashion to what they typically call a stream, I would call it a log, and then have the reader on the other side pulling that data off and going and processing it. Again, enabled by the fact of the higher speed technologies, higher speed capabilities to do this, and the consumer on the other end. The next couple things, the replayability. All of these systems, the real-time analytics, the streams, and so on, generally they're built in large scale-out distributed systems. Large-scale distributed systems, typically, I don't want to say they're unreliable, but they're typically built on top of commodity systems. And if you will pardon the term, shit happens. Machines crash, networks go down, a disk crashes, whatever. Well, you can't very well have your system die when a single node crashes. You need a way to say, okay, I've temporarily lost access to some data, start that up again, and keep going. Well, what's great about a log? Well, I keep getting data in, but I've crashed and I've stopped processing it. Well, I'll start up again and I'll just pick up right where I left off and continue processing. So I can replay events that may have come in, while I was down, and I can just go forward and keep replaying them. And that's a key part, especially with some of the streaming and the analytics, because they are able to take checkpoints on any failure. They go back to the checkpoint, restore their state, and continue. So it's a very nice fault-tolerant story. Same thing with the distributed systems. Once you have those kinds of capabilities, you can have many systems that are running a different part of the analytic engine distributed over a wide variety of systems. And they can all be reading from the tail of that log, going and processing that data. And again, that paradigm very much makes that simple because each one of those applications doesn't need to worry about the coordination and everything else. That's down in the log storage system itself. They just see it as that stream of data. And microservices are a bit of, they're not necessarily an outcome of all of this. There are other things driving towards microservices, but microservices are basically encapsulating all of this is you have these very small services that are designed for one purpose, communicating with other microservices over a message bus or a log style communication, where they're decoupled from each other. They can send the messages, push it on a log. They know it'll be consumed by somebody on the other side or consumed by multiple microservices on the other side. But what it allows you to do is to decompose an application to these very fine-grained functional chunks, each one of which is much simpler and easier to understand, design, develop, and debug, but still have the whole application have a huge amount of sophistication and complexity, but really composed out of those small building blocks. And all of these things really come out of, or really can make use of, a log-based storage system to handle those communication. So what are we looking at here? As mentioned, communication. Logs can be on the one side, data is being pushed into them, analytics engine or something else that's reading from them. It could be reading from one log, it could be reading from multiple logs. It itself is doing, whatever. Where is it writing its data? It could be writing its data nowhere, it could just be available for query, or it could be writing the results of its analysis, getting processed down the line by yet another job. So a very nice decomposition, and the logs can provide that communication. What's the value about a log for communication there? What happens when something fails? Let's say instead this were a TCP connection, and this process over here failed. What would happen to that data that's written by those gears, by that process? Well, he's going to try to write it out over TCP. He's going to get a broken TCP connection. He's going to have to figure out, okay, well, where am I trying to write my data now? He's going to have to wait till that guy comes back up. If the other process moved machines or IP addresses or anything, he's going to have to know about that. A lot of complexity builds up in there. In this particular case, he doesn't have to worry about it. He writes the data to that log. It's persisted right there. Eventually, that process will come back up, and as life goes on. Same thing again, if it's the gear process that fails instead of the question mark. You don't want to deal with the broken TCP connection and everything. The logs really decouple it. They provide that persistent communication, and they allow those processes to fail independently, to restart, and so on, and really minimize the impacts on the rest of the system. Now, let's take a slightly different example. If you notice here, those gears change from blue to green. What does that mean? It means I like different colors. No, what it really means is maybe I've upgraded that system. Maybe I've moved it to a different, faster machine. Maybe I've debugged it and I'm rolling in a new version of it. Does my question mark guy need to care? Again, you get them decoupled. What I can do is I can go in there and I can say, okay, I've got my blue systems in there. I can shoot it. This guy, when he comes back up, he can say, okay, I'm going to restart. Maybe he's going to start right from where the blue guy left off. Or maybe because I know the blue guy had a bug, I'm going to go back a week or a couple of days and process information again, this time with the correct algorithm. So I've got different possibilities for how I do this, and I can use the fact that the logs are persistent, and they're not just persistent for the tail of it. I can go back in time and repeat operations as necessary and redo the operations. Now, clearly, I'm glossing over a few facts here. Specifically, if I am going back in time and reprocessing operations, I don't want to confuse the next guy in the chain by having, results written twice. I need to look at the logs, look at the processing there a little bit, but you can basically see, the general style of how this would work. There's a question there.
Where do you get the metadata to reassemble the logs? Where's the metadata?
Yeah.
Are you going to cover that?
I will talk about that. The basic question was, where do I get the metadata to basically know where I am and so on? Break them up, put them back. That comes from checkpoints and things like that, where I do keep some information about the state of the system. It's a lot less information than I need with like a recovery log in a database and so on, but I do need some information about the state of the system to allow me to do, basically start up again in a sane state. The other interesting thing is, here I've got both the green and the blue running together. This is, I think, one of the interesting applications. What if I want to do an upgrade of that system, but I'm not really sure my upgrade works yet? Well, I think it does, and it's passed all the tests and so on, but I'm not quite ready to commit to it. Run them both. Run them both off the exact same inputs. I can compare the results at the end by that second level processing. If they're either matching or if I'm seeing that the green processing is giving me better results, more accurate, however you define that, I can switch over to it when I'm comfortable that it's really up and running fine. What happens if my green pipeline at the bottom there is showing problems? It's crashing, every 6 hours due to whatever. What have I lost? Hopefully nothing. Hopefully at this point I haven't yet trusted it, and I'm still basing my business on the blue pipeline. But this way I'm guarantees that that green pipeline, it is being tested on the exact same data with the exact same input rates, et cetera, so that when I finally decide, yes, I've seen enough, I'm confident in it, I've got a very high degree of confidence. The other thing about this would be it allows a lot of flexibility in terms of future-proofing. That blue job I have there, I designed it, a year or two ago when my business had certain characteristics. Things have changed. I'd really like to analyze the, parts of the business in a different way that I didn't think of before. I don't actually necessarily need to go and add new complex logic to that blue processing chain. If it's, dependent on exactly how it works, it may be easier. I can simply add in a new processing engine to add in the new analyses, leave the blue one alone. Is that always realistic? Not always. Sometimes there may be reasons why you really want to combine the analyses together. It may be more efficient and so on. But in certain instances, you could imagine you want to leave the existing job alone and add in a new one. And maybe you want to add in a new one because once a month you process everything and you redo a different form of analysis. Or it's just a totally different answer you're looking for, and the two really have very little relationship, but they happen to use the same source data. So it gives you a lot of flexibility of what you can do and how you can expand out to address new and changing business needs. This is a pattern which, especially for microservices and so on, kind of really captures the nature of how you can use the logs in these formats. It's called the CQRS pattern, the Command Query Responsibility Separation pattern. And the basic idea behind this is that as you're making changes to a system and you're processing, the commands, the format of the commands and how you record the behavior of the commands tends to be optimized differently than how you'd like to look at that information. An example of that, I tend to think of warehouse examples and so on. If you're a warehouse processing, you're receiving orders from your customers, you're going to be looking at that. You're going to want them organized by, the order, when you're expected to ship it. You're going to want to know which warehouses are going to process that order and so on. If I'm a customer, how am I going to want to look at it? I'm going to want to look at it based on what are all of my orders? How far back in history do I want to go? I don't really care necessarily which warehouses they're coming from, or the fact that, I'm getting 3 entries from one warehouse and you guys are getting another 10 or so on. From the customer point of view and how I'm going to query it, and I'm going to want that information organized in a different fashion. And by separating out that right model of how you store the commands optimized for that side and how you're processing them on the read side due to how they're going to be queried, you can separate those two out and get efficiencies in how you handle those two situations, such that I, as the customer, when I come in and query, I can get the information quickly because it's already stored in a format that's convenient for me. And in between them is that event log, that basically log where I record, here are the changes, and then on the read side, I can process those changes and I can store them in any format I want that's optimized for how it is going to be queried. So let's take a look at an example, how you kind of build something up, how this processing and how this style can really make your life easier. You have a microservice, it's running, I don't know what it's doing, but it's creating a bunch of changes. And again, maybe it's an order processing microservice, it's getting commands in from a REST interface, or maybe it's, business to business and it's gotten commands in that say, okay, we need to reorder because some business is running low on inventory, whatever. And you have query microservice on the other side, which is reading that information, building up an internal state machine optimized for how you're going to query that information. And there are all sorts of different ways you could do this. That could simply be like an in-memory hash table or something like that. Why in memory? What about persistence and so on? Well, it's all persisted in the log. It can truly be an in-memory data structure, very, very fast to access, and you rely on the fact that all the complex nature of storing the data and so on can be handled in the log. How much data are you going to store? Are you going to store all the data from the log? In some cases, maybe. But again, think of like an order processing system. If I'm coming in as a customer and I want to look at my orders, do you think my primary interest is in things I ordered a year or two ago? Probably not. I'm probably mostly interested in things I ordered in the last week or two. So that data structure could be optimized that it only keeps 2 weeks worth of orders. And maybe I have a button at the bottom of the screen that says, if you want to see more, click here. And then something else starts up which can go backwards in the log and process a longer distance back in time. It's going to take longer, but it's optimized for the fast and frequent query of, tell me what I've ordered in the past, the past 10 orders I made or the past 2 weeks or whatever. So, what happens when there's a failure? Well, I restart the process. Could be on the same node, could be on a different node, doesn't really matter. And what does it do? It reads the log. Now, theoretically, the simplest and easiest answer would be it just starts right at the beginning of the log, rereads the information. As it rereads the information, it rebuilds its data structure. What's the state of the data structure going to be when it's processed the log? Exactly what it was up there. It's processed the exact same information, doing the exact same operations. Now, realistically, that log could be quite long. How long is it going to take to read the whole thing and reprocess it? In a lot of cases, probably too long. You really want that process to restart quickly. And that's where you get into things like checkpoints and so on, where periodically you could basically, snapshot your hash table, write it out to disk in a format that says, here's the serialized information, here's the position in the log, any other information you need to know. So when I restart, I simply bring it back up, I take a look at that checkpoint, reinstantiate my hash table, start reading from the log at that point. Now, a question for you, if you've ever done, recovery logs in databases or file systems or anything else, that can be pretty complex processing. This process here, it restored from its state from that checkpoint, so it's got the hash table back in memory, and it's reading from the log. Again, it's moved back in time somewhat. What's the recovery logic it has to implement? Well, is it recovering? Is it recovering or is it reading new data? And what's the difference? As far as it's aware, it was just a happily running process, and it's picking up and it's processing the data. There's no complex recovery logic. He reset the state of the world, and he just picks up and continues. Doesn't even have to know if it was a crash or anything else. No complex recovery logic really makes the job of that application writer simple, because he can guarantee he gets replay the exact operations in the exact same order with the exact same results. Okay, different situation. Again, we have our same little query microservice, getting a whole bunch of changes in, but for whatever reason, the query load is just going nuts. Whole bunch of different people all querying the information. That poor process is starting to slow down because it just can't process it all. Okay. Who says we have to have one? Let's clone it. We could have a special memory operation that clones it, or those other new microservices can pick up from a checkpoint, start processing the log. Now we have 3 copies of that same application. All 3 of them can process the exact same sets of queries. We've tripled our query bandwidth at this point. Now, this doesn't quite tell the full story, because this is assuming that the query processing is the bottleneck in the system. That all 3 processes can be running, keeping up with the log and the full set of changes within it. What if the problem were instead that you can't keep up with the rate of changes in the log? So you're falling further and further behind. The answer to that? You can actually partition the service. You can have those 2 new instances, one of them process half the results, the other one process the other half. And in fact, what you could actually do in the log itself, and systems like Kafka and Pravega support this, you can actually be partitioning the log itself. So that request A through M on the one side, those are the only requests it ever sees. And the other one only receives those commands pertaining to that set. So you've partitioned your data set, and this is where especially running these operations in distributed scale-out systems makes a lot of sense, because you can partition your process across all the instances or all the machines in your system, processing a different part of the log. Obviously, you need some load balancing and things like that to direct queries to the appropriate node, but each one is only handling a small subset of the operations. In terms of application design and coding, how much difference is there between that application down there that's processing part of it and the application above that's processing all of it? Any logic difference? Not really. And it does assume that the operations are basically, distinct from each other, that an order for me doesn't affect an order for somebody else. So there are some dependencies on the data that you need to be aware of. But in terms of the basic application logic, it's no different if I'm processing everything, if I'm processing half of it, if I'm processing 1/10 of it. In fact, I don't really even have to know. That can be decided outside of me by the overall system that partitions and so on and distributes the nature of this. And I can simply be aware that I'm receiving events, I process them, and I respond to queries. So my application can be coded in a very simple fashion, and suddenly I have a distributed scale-out application that I, in essence, get for free. And that's, I think, a real benefit, because distributed scale-out applications traditionally are very hard to do correctly. And this makes it much, much simpler. Now, of course, once we've partitioned it, we don't actually need that original one anymore. We could get rid of it. We simply have the 2, 3, 10, however many instances that we need processing that data. Now the next question is, what's a query? Everything I've kind of presented before, I've presented a bit from the example of like a warehouse application, and I am coming in and I am looking at that data because, I'm the customer and I want to look at it. But really, what's the difference between a query and a read? None really. A query is just a form of read that presumably, was initiated from an outside entity. Again, I could have some of these processing engines, Flink, Spark, Apex, and so on, working with a partition system where they're reading that data and processing it, coming up with answers. Again, real-time analytics, because once I have this log, my latency between when those events were generated and when I'm able to receive them and do something with them could be on the orders of tens of milliseconds. And at that point, you're basically looking at real-time analytics processing that data. But it doesn't just have to be real-time analytics. This supports batch processing also. If I want to go back in time and read a month's worth, I can do that. A lot of interesting things I can do when I have this model. And again, I don't necessarily need to have all of this decided up front. I can start with a certain analytics job running on this. I can add more over time. I can spin some up temporarily to process a batch of entries, spin it down, spin it up later. A lot of flexibility in how I do this, because basically I've been able to separate the data model of how the data in the log versus the processing of it. And by having that split, I have a lot more flexibility in how I process the data and what I wind up doing with it. So the final thing to look at in my mind is, okay, we've talked about log storage. We've talked about how it can be the basis of this new style of distributed scale-out applications. Is this really log storage? Isn't this just storage by a different name? And I took a quick look at basically what are the characteristics of log storage? How do they compare with some of the characteristics of existing storage? And I'll walk through this, but ultimately, as you can probably guess, my answer is going to be log storage doesn't really match any of these perfectly. And it winds up being a combination, which is why I think it really is a different class of storage, optimized for some of the particular use cases of a log. Way over on the side is block. Block is really, really great for fast IOPS. You can read and write, very low latency on the individual reads and writes and so on. Problem with block, on the other hand, is, especially from an application point of view, it's a bit of a pain in the neck. The application has to do everything. Block just provides this bag of blocks, and it's a pain in the neck to use, but it's very, very fast. File systems typically work on top of blocks. File systems are very nice. They provide nice human-readable interfaces. You can look at files and so on. You can navigate through them. They're typically built on top of block. They're typically slower because they do have those extra levels of indirection with files and so on, directories, etc. Slightly better for sharing. You can share them more over, CIFS and NFS or SMB and NFS and things like that over a local area network. Object systems are kind of the next scale. Again, great for humans. They have these nice readable names and things like that. Where the data is stored, in a file system, the application typically has some input into that. How it actually lays out the directories and things like that will have some impact on where they get stored and on the retrieval characteristics. In an object storage system, that's all out the window. Every object is independent. You don't know where it's going to be stored. It could change over time and so on. But object systems are great at two things. They're great at sharing on a global scale. They're typically based off REST protocols, HTTP access, and so on. Very good for across firewalls and global scale. They're also typically great at high number of concurrent connections. So it's like a block system, very, very fast, individual I/O operations, lightning fast. In an object storage system, individual I/O operations typically are not that fast. There's typically a very high latency in even accessing a single byte. But because an object system is normally scale out, where it really shines is when you have 1,000 or 100,000 or 1,000,000 concurrent operations running in the system. The object storage system can partition those out, distribute them throughout the system, and get huge amounts of bandwidth and throughput across the all those connections. If you have an object storage system with one application, with one connection, your performance is going to be terrible. You can decompose it so your application has 10,000 connections that can operate in parallel. You're going to have great performance. So how does that relate for a log? A log, I put it here as human accessible. Again, that's a little bit arguable. It depends exactly what you mean. But what I mean by that is, a log is it's a format that a human can understand, that ordered sequence of events that you can just read A, B, C, D, E, and so on. Maybe the actual events themselves are stored in binary or something like that, but they could just as easily be stored in JSON text or something else that truly is human readable. You do have a degree of sharing. Again, you don't typically have the sharing at the level of an object storage system. I've not yet seen a log-based system that really allows access across the globe. But within a data center or so, very much you can imagine cases where multiple different applications are reading from the same set of logs, doing different processing. So they need a level of sharing that's more like a file system and how far it can share. It does need to scale infinitely. Depending on the nature of your system and so on, you may want to store years of data in your logs, just depending on how you're doing it, the retention, what other properties there are in the system. So it needs a huge amount of scale like an object storage system. For recent data, for all those appends to the system, and for real-time analytics and so on, all those reads from the tail of the log, those are very fast, high IOP rates. There's not much data necessarily, but it's a lot of individual IOPs sending small amounts of data either to the log or reading it from the log. So in that sense, a lot like a block system. Very fast IOP rates at that tail of the log. But how about some of what we call the catch-up reads? When there was a crash, maybe part of my system was down for a few minutes and it goes back in time. There, I really want a fast bulk read. Also the case for situations where, again, I'm doing a batch processing job and I'm going to process a month worth of data. I don't want to drib and drab that data in for the entire month. I want it to give me give me 3 or 4 megabytes worth of data all at once and I'll process the events. So I want a much more bandwidth-oriented, bulk-oriented interface when I'm reading from not the tail of the log, but when I've gone back in time and I'm reprocessing. And that's more akin to an object system or a file system that more supports that fast, high bandwidth reading of the data rather than necessarily a block storage system. So as you can see, logs, they're not truly unique. They share characteristics with these other systems, but basically to really make this work, it's not just one of those systems. It's a tiering or other things like that to try to combine the best properties of those other systems to build the best log processing system. Because those characteristics are really different based on when you're at the end of the log or when you're doing the catch-up. And it really combines some of those different features. So to summarize, what does log-based storage allow you to do? It decouples your data from your applications, gives you a lot of freedom about how you design your system and how you can adjust it for the future, expanding the system and so on in ways you may not have anticipated when you started. It allows multiple applications to read from that same source data, and again, those secondary or tertiary applications may be ones you didn't even initially consider, or maybe testing or other things like that. HA, recovery, replication, and so on can be handled at the log system itself, simplifies the job of the application. The application has to be concerned with reading in the data and processing it, but it doesn't need some of the complex logic that you need when all that functionality is embedded in the application. The log and its persistence can handle a lot of that, make the job of the application writer simpler. Does great source data for streaming analytics, and it's got some different characteristics than block and file. It combines them in some different cases, but it really does speak for a new paradigm, a new construct specifically around log-based storage that can really satisfy those characteristics. So I do have, at least by my watch, about 5 minutes, I think, before the session is supposed to be over. So you can open it up for questions at this point. Because before I do that, I just say thank you for your attention. Appreciate it. And if you have any questions, I'll be here. If we run out of time or anything, feel free to catch me the rest of the conference.